Welcome back to a new video about LC ladder filter design. This is our example number 5, where we continue with the elliptic response filters. In this case we will discuss the design of a band stop filter. So we will work out the calculations step by step and also verify these in SPICE simulations. So let's look at our example. The objective is design an elliptic response filter of an LC ladder configuration of a band stop filter, and we need to use 50 ohm double terminated shunt input circuit. Now, we have discussed this many times in the previous videos, that we have a generalized filter we need to design, and there is a normalized source resistor and normalized load resistor, each 1 ohm. And we also have these specifications for our filter, like maximum passband ripple, minimum stopband attenuation, and also lower passband frequency, upper passband frequency, and the lower stopband frequency and upper stopband frequency. These 6 specifications will be checked after we have designed this using the simulator. This A max here is also here in the elliptic response, given as the reflection coefficients. Okay, let's look at the solution. The first step is the passband bandwidth, omega bandwidth, and also the center frequency for this specification. We have then the bandwidth as the upper minus the lower passband frequency. That's also 2 pi times the upper and the minus the lower passband frequency from the specification. That will be then like this, 288 pi times 10 to the power 3 radians per second. Now we go to the center frequency, which is the geometric mean of the upper and the lower passband frequency. We do then 2 pi times the square root of the upper and the lower passband frequency, given here in hertz. So that can be then calculated like that, and that can be then determined as 6.72 mega radians per second. Step 2 is the normalized passband frequency and also the normalized stopband frequency, each with a capital letter omega, and here omega also, of the prototype low pass filter, because we will convert our low pass filter design, the circuit, into a band stop filter shortly. This is the expression for the normalized passband frequency, which is the bandwidth divided by the difference between the upper and the lower passband frequency, which this is always of course 1, because this value is exact same as the denominator. That's just 1. The interesting thing is actually the normalized stopband frequency. That's then the bandwidth divided by the upper stopband frequency minus the lower stopband frequency. That will give you 2.4. Now the step 3 is the band stop scaling factor, KFBS, for BS for band stop. That is just the bandwidth we have this determined in step 1. So that's just 288 pi times 10 to the power 3 radians per second, which is also 144 kilohertz, which is just the difference between these two values. Step 4 is one of the important steps again, the filter order N. That is required, that is determined actually from the required transition sharpness, and also the minimum stopband attenuation we have here is 25 dB. Now, that is what we have. We have now the transition sharpness, omega R is equal to omega S over omega P, which is then 2.4 over 1, which is just 2.4. This is the maximum allowed transition sharpness. You can go lower, but this is the maximum allowed transition sharpness, and we need to have a minimum of 25 dB attenuation. Now, looking at a table, this is a table from the elliptic response for a third order. You can recognize here also the ripple is given as we want it for this example, that we have a region here which said that there are some options, some candidates to use this table for our design. You can, for example, look at row 7, that the sharpness here in this column is 2.3662, which is smaller than 2.4. That will do the job. You can also see that it's 28.89 dB as a minimum, so that is also according to the specifications. If I go up, for example, to row 6, then the sharpness will go up. That means it is not allowed anymore. Of course, the A minimum is even better, but this is not fulfilling the specification, so we need to fulfill this column and also this column for A minimum. If I go down, row 8 will also do the job, because again, according to specifications, 2 specifications, sharpness and the minimum, A minimum, and also the row 10. But if you go to row 11, you see that the sharpness is even better, but I have now 24.88, which is less than 25 dB, so this is also not allowed. So I can choose between these 4 rows, set of normalized values, to design the circuit. So we need to have, looking at this specification and also the table, we need a third order filter. Okay, now bringing up the candidates 7 up to 10, the row 7, 8, 9, 10 here, we can choose one of these rows as our design. Now, to satisfy the requirement of both the maximum omega R of 2.4 and the minimum stopband information of 25 dB, we can choose, as I said before, between 7 and 10, the rows. I just pick the first one, which is just row 7. You can also take 8, 9 or 10, it doesn't matter. Okay, that means I will check this. These are then the normalized component values I will use in my design. Okay, these are the 3 parameters I will need shortly in the calculations. So for the center frequency, the scaling factor for the bandstop filter, and the Km, which is 50. Why? Because we need to go from 1 ohm to 50 ohm as set in the objective. Now, the low pass to bandstop transformation. This is the low pass filter for the elliptic response circuit. You see here the C1, C2, C3 and the L2. That is actually also this one, because C1 and C3 are exact same. And the values are here given. These are the normalized values in farads. That's also for C2, which is this value, and L2 has this value, 1.0006 Henries. Of course, they are not practical, but we will make it more practical going to the specifications. The transformation from this low pass filter to the band stop filter is going like that. So you change every capacitor in a series capacitor and a series inductor. And every inductor must be then changed into a parallel inductor and a parallel capacitor. That means I have to then change this circuit in this circuit. You see actually here the capacitor is changed in a series combination of inductor and capacitor. That's also shown here. That's also shown here, and this notation means actually LS, which is series due to C1, and the capacitor is series due to C1. So this C1 will produce these 2 components. Similar for C3, similar to C2. And this one, because it's an inductor, will then make the parallel inductor and parallel capacitor. So now we need to use this circuit and then calculate the required components. You also see that RS and RL are primed, so that means they are also scaled up from 1 ohm to 50, 1 ohm to 50 ohm. Okay, let's bring this here and then calculate the scaled component values for our final circuit or designed circuit. And the first one is this CSC1, which is then this. We need to use the band stop scaling factor, the magnitude scaling factor, and also the center frequency, and also the C1 from the table, which is here in 0.9339. Now when you do the calculation, you get here 374.2 picofarads. And in a similar form, but then for the inductor here, then you need to use the magnitude scaling factor and also the band stop scaling factor, and also still the C1, same thing. There you get 59.17 microhenries. In a similar form, you can do that for CSC2 and LSC2 in a similar form, and then also CSC3. That's exact same as CSC1, because you see they are exact same also in the normalized values. That means also for the inductor is exact same. We'll continue now with the final 2. These one LP-L2 and CPC2, CPL2. I mean, that's actually here. So 22.09 nanofarads, and the other one will give you 1.002 microhenries. And I said before, the RS will be then 50, RS prime, and also the RL prime will be 50 because the Km was 50. Okay, now we have our components. Now, bringing the components all here, this is the summary of the results. This is the circuit. Now the design circuit in the simulator is this. You see the first one, which is our prototype low pass filter. And this is now the designed band stop filter, which is scaled up and also transformed from low pass to the band stop filter. You see also the values here. You see also the RS and RL of 50. And also you can check the values here from here, and you can see that they are all here. Let's now check that this circuit will do the job for our specifications in the simulation results. Okay, this is now the body plot for the gain only. You see some labels, so I will go one by one. You see this first label, which is the lower passband frequency, which is at 1 megahertz. There you see the gain of minus 6.1151 dB, and the baseline here is minus 6.02 dB, because that is the gain of 0.5, because you have a 50 ohm here and 50 ohm there, so we have at the passband gain 0.5 dB, which is then 20 log of 0.5 is the minus 6.02 dB approximately. That's shown here. And if we now look at the difference, that will then 0.0945 dB, which is less than this. So that is according to specifications. The upper passband frequency, you can see at 1.144 megahertz. There you see the gain is minus 6.1234 dB, and going from the baseline again, which is then minus 6.0206 dB, which is then in this case 0.1028 dB, which is larger than this one. So it is close, but it is not that as expected. So it is, you can say this decent, is fine for all practical purposes, but this may be something we need to consider in future actual realization of the circuit. But still not a very large error, just a small error here. Looking at the stop band attenuation, the lower one, you see here the value of minus 32.92 approximately, and then going down from the baseline here again, that's then 26.9 dB, more than 25 dB minimum what we needed. And for the upper stop attenuation at 1.1 megahertz, you see here 30.4 dB approximately, so definitely more than 25 dB. So it's all according to specification. These three are according to specification. This is close to specification. You also see this one, that is actually our center frequency, and that can be calculated actually using the omega center we have used, which was 6.72 megaradians per second. You can convert that to frequencies in hertz by divided by the 2 pi, and it will give you now this value, which is then 1.0696 megahertz, which is exactly as we have here. So this are actually the center frequency. You also see that the minimum attenuation for this filter will be always 28.9 dB, which is then exactly and also much larger than the 25 dB we needed. So we can say everything is according to specification except this one. So we can say this is perfectly fine for all practical purposes. Okay, this is now our example number 5 concerning the elliptic response using the LC ladder filter configuration for our bandstop filter. If you have any questions, comments about this example, please let me know. I will try to answer them as soon as possible. See you next time in another interesting video.